Good morning. Good morning, all. Today we are going to see about medical application of lasers. Outcome. After completion of this section, the students are able to explain the medical application of laser. The highly collimated beam of laser can be further focused on a microscopic dot of extremely high energy density. This make it useful as cutting and cauterizing instruments. Lasers are used for photocollation of retina to hold the retinal hemoglobin and tracking of retinal tears. The higher power of lasers are used as a cataract surgery if the suppurative membrane surrounding the implanted lens becomes milky. The photo disruption of membrane often can cause drawback like a shade almost instantly restoring vision. The medicine have two prime objectives. First, to detect the disease at an early stage before it becomes difficult to manage, and second, to treat it with high selectivity and precision without any adverse effect and involved tissues. Lasers are playing a very important role in the pursuit of both these objectives. Due to their remarkable properties, lasers have made possible ultra precise, minimally invasive surgery with reduced the patient trauma and hospitalized time. The laser spectroscopic techniques have to promise to provide sensitive insight near the real-time diagnosis with biochemical information on the disease. This development have the potential to change the way medical diagnosis presently received. Laser and tissue interactive. The radioactive and non-radioactive relaxation imagine an excited molecule that is alone, without any other nearby molecules to interact with. In the case, two things could be happen. First, the energy gained by the observing photons and initially stored in the one mode will begin to be shared out between the all modes, a non-radiative process of intramolecular redistribution until the molecule is in equilibrium. However, the molecule could also jump absurdly to a lower energy state emitting photons. If the radioactive lifetime of molecule is shorter than the redistribution time, then it is likely the photon will be emitted before the process of intramolecular redistribution has completed. There are two possible radioactive processes, fluorescence scene and phosphorofluorescence scenes. During the fluorescence scene, there is a transition from state similar state. As some redistribution will always take place before a photon is emitted. The energy of their radiated photon will always be lower than the absorption photon. The fluorescent scene and phosphorescence. During the fluorescence, there is a transition from state to similar state. The phosphorescence occurs after the intramolecular system crossing takes place, so transition accompanying the radiation typically involving a change from the triplet to single state, which much less likely to occur, and so radiation is of lower energy and occur over a much longer time scale. Photochemical reaction. When the light absorption gives the rise to an electronic transition, the more energetic electron will an average orbit of nuclei at the greater distance. As the attractive nuclear force falls rapidly with distance, The electron will be less tightly bound, will be able to form chemical bond with another molecule more readily. This is the basis of photochemistry. Thermalization, collision, relaxation. While an excited molecule is undergoing intramolecular redistribution might collide with another molecules, some of the vibrational energy in the excited molecule will transfer to the molecule as the translating kinetic energy. The molecular translation kinetic energy is what appears at the macroscopic level as the temperature rises as leads to photothermal effects. This process of collisional relaxation will thereby thermalize as absorbed photon energy in the matter of picoseconds.